Hello friends, this is Dr. V. Sivanagaraju, AC Department from IARE. Today's topic is generation of DSBSC waves. Already we discussed DSBSC means double sideband suppressed carrier. Now how to generate this DSBSC? We are using generally two types of modulators. One is balanced modulator and another one is ring modulator. So today we are going to discuss about the generation of DSBSC. Let us come to the topic. So we used two types of modulators. One is balanced and then is the ring modulator. So this is the block diagram of the balanced modulator. So here we are having two standard AM modulators. Two standard AM modulators and one local oscillator and another one is the summer. So in the upper channel we are giving M of t, whereas in the lower channel we are giving minus M of t. Means here we're using the two modulators are identical, but the sign what you're giving the input is different. Remaining all are same. So here our aim is to suppress the carrier. Why? This carrier uses more bandwidth and wastage of transmitted power. So that's why we are going to suppress that carrier by using these two standard modulators. So in the time domain description, we already seen that the modulated signal of DSB is just the product of C of t and M of t. Okay, so again we are going to see this picture. So in this picture we're having M of t is giving. So after giving M of t, this AM modulator which produces S1 of t, and in the lower channel again another AM modulator which produces S2 of t. These two signals is going to giving this summer, that is the final output of that summer is S of t. So S of t is equal to S1 of t minus S2 of t. So here S1 of t will represent as AC of 1 plus Ka M of t cos 2 pi fct. So what this one? This is nothing but amplitude modulation. S of t which is equal to AC of 1 plus Ka M of t cos 2 pi fct. This is the standard AM equation. Again in the lower channel S2 of t which is equal to AC of 1 minus Ka M of t cos 2 pi fct. Why? In the lower channel we are giving minus M of t. So that's why here the sign is changes in S2 of t. Why? We're using two standard AM modulators. So it produces same that AM modulation. Now these two outputs are given to the summer. So the summer which produces the output is S of t which is equal to S1 of t minus S2 of t. So finally what you get? 2AC Ka M of t cos 2 pi fct. So here we are going to write what is S1 of t and what is S2 of t. Okay, so S2 S of t which is equal to S1 of t. So what is S1 of t? AC of AC of 1 plus Ka m of t of cos 2 pi fct. This is our S1 of t minus S2 of t. Again AC of 1 plus 1 minus Ka m of t cos 2 pi fct. So these are the S1 of t and S2 of t. Okay. So here I am expanding this equation. AC cos 2 pi fct plus AC Ka m of t cos 2 pi fct. Again here minus sign is there. So minus AC cos 2 pi fct, and again the inner bracket again minus. So minus of minus plus. So plus AC Ka m of t into cos 2 pi fct. So in this equation we're having AC cos 2 pi fct and again minus AC cos 2 pi fct. So both are going to cancel each other, and finally what you got? 2 AC Ka m of t cos 2 pi fct. So this is our output of the summer, 2 AC Ka m of t cos 2 pi fct. So in this picture we are having no carrier, that is we are going to suppress the carrier. Again we can see the standard equation, AM equation. What is AC of 1 plus Ka m of t cos 2 pi fct? So the standard AM equation is AC of 1 plus Ka m of t cos 2 pi fct. Okay, so again you can expand this one. You got AC cos 2 pi fct plus AC Ka m of t cos 2 pi fct. So in this picture we're having AC cos 2 pi fct. AC cos 2 pi fct. This is the carrier signal. This is going to suppress. Actually this is the standard AM. Okay, so in standard AM equation we are sending carrier as usually. So this carrier wastages our transmission power and it uses the bandwidth. So that's why we are going to suppress this carrier. So that's why the name double sideband suppressed carrier. So now we can see this S of t. What is this? Is DSB suppressor carrier. In this equation, that AC cos 2 pi fct term is missing. Okay, so that's why we are going to suppress the carrier. Okay, so in this S of t is in time domain. In time domain, it is called S of t. We are taking a Fourier transform on both sides of this equation. It is converted into frequency domain. So S of t, which transfers into S of f, time domain to frequency domain. So S of f, which is equal to AC Ka m of f minus fc plus m of f plus fc. So we are going to applying Fourier transform for this equation. Generally, what you got when you apply the Fourier transform of the right hand side of this 2 AC Ka m of t cos 2 pi fct, you get AC Ka by 2 of m of f minus fc plus m of f plus fc. So the numerator having 2, again denominator having 2. So both are going to cancel. Finally in S of f, we are having AC Ka of m of f minus fc plus m of f plus fc. Okay, So this is the output of double sideband suppressor carrier from the balanced modulator. Okay. So here we can see the spectrum of double sideband suppressed carrier. So the carrier is missing. Okay. So another one is the ring modulator. So by using this ring modulator also, we are going to produce double sideband suppressed carrier. Okay. So here we used 4 diodes in the form of a ring. Okay. And we are giving a carrier C of t. So this carrier C of t, which is having high frequency and high amplitude than the M of t. Okay. So the ring modulator consists of 2 transformers. One is input transformer and another is output transformer, and having 4 diodes which are going to connect it in a ring circuit or bridge circuit. Okay. So already shown in the figure. Now the operation. So how this circuit is going to operate. When the carrier is positive, the diodes D1, D2 are forward biased, and the diodes D3 and D4 are reverse biased. Why these 4 diodes are we are placed in a ring. So 2 diodes is going to on. Forward bias means it is going to on. Hence the modulator multiplies the message signal M of t by +1. So what you get the output? V naught of t is equal to M of t. Okay. When the carrier is negative, the diodes D3 and D4 are forward biased, and diodes D1, D2 are reverse biased. Hence, the modulator multiplies the message signal M of t by -1. So that is V of t, which is equal to minus M of t. That means the square wave carrier signal C of t, which drives the 4 diodes, depends on the carrier signal. The diodes are going to forward biased and reverse biased. Okay. So we can represent this carrier signal by a Fourier series as C of t, which is equal to 4 by pi of cos 2 pi fct minus 1 by 3 cos 6 pi fct, and so on. Now what the output of this ring modulator is S of t, which is equal to the product of carrier signal and message signal. So here we are going to substitute the C of t in the modulated signal. That is S of t is equal to C of t into M of t. So we are going to directly substitute this C of t. Just multiply. So 4 by pi cos 2 pi fct into M of t. Again in the second is minus 4 by 3 pi M of t cos 6 pi fct. Okay. So this is the ring modulator output. So again we take the Fourier transform of that S of t equation. We get S of f. Okay. So here we're getting 2 by pi of M of f minus fc plus M of f plus fc minus 2 by 3 pi of M of f minus 3fc plus M of f plus 3fc. Okay. So this is the frequency spectrum of this double sideband suppressor carrier by using that ring modulator. Okay. So here we can see this picture. M of t is the message signal, C of t is the carrier, So depends on the carrier signal. Here the diodes is going to on and off. So when the carrier is positive, then diodes D1, D2 are in forward bias. So that's why it is going to on. So in the green color, which indicates this D1, D2 are going to on. When carrier signal is negative, this D3, D4 is going to on, and D1, D2 are going to off. So finally, you get that picture. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.